Hello everyone, welcome to today's webinar. We are going to be tackling everything about corridor optimization, what it is, how to do it, and why you might want to use it. For those of you here in the live version of the webinar, please, ask us questions, engage with us throughout the presentation. You can use the Q&A section of your GoToWebinar panel, and we will tackle the questions at the end. So as we get started, here's kind of our plan for the next hour. We might be a bit shorter, which actually would be a first for a webinar with us here at Softree. First, I will take a few minutes to talk through some, optimization concepts. Then I'm going to pass it over to Matt. He's going to be doing a live demonstration, and in here he's going to set up our terrain model, input preliminary alignments, add constraints and control points, configure our costing model, and then conduct a vertical optimization, do a little bit of a cooking show approach on horizontal optimization, and then show you how we can compare alignments. So we are going to be using our RoadEng software with Softree Optimals. This is kind of like our biggest, fullest package of software today. I should make a couple notes about that first. So RoadEng is our corridor-focused civil design software. It's got 3 different modules. Inside the location module is actually where Softree Optimal can be available as an add-on. So that's what we're working with today. I should mention it is also a standalone product. So in standalone Softree Optimal, the workflow that we are going to show you today is pretty much identical to once we get into the location module of RoadEng, apart from the terrain surface creation. So in standalone Optimal, it does require a pre-built land XML surface. So standalone Optimal, it can be used in conjunction with other civil design software like Civil 3D. We even actually have an export tool plugin that you can use with Civil 3D to help you get your cross sections and sub-assemblies out of Civil 3D and into Optimal. So that's a little bit on the software side, but more importantly, let's talk about what is corridor optimization. It is a mathematically based process that determines the lowest cost alignment that meets the constraints and standards that you set up within the software. It's based off of a mixed integer linear programming optimization engine. And it really, we actually kind of joke in our sales team, it's kind of like one of those Staples easy buttons. It truthfully, it's not one click, it's a few clicks, but it's not that far off. It's turning the road design process into a semi-automated one. And if you're someone who is, interested in, say, for example, internally balancing the mass haul of a road, this is where, that semi-automated process can save an absolute tremendous amount of time. Now, optimal and optimization are not suitable for all road projects. If you have a heavily constrained urban alignment, driveways every 30 feet, we would likely recommend don't even try because optimal is not going to have any room to move the alignments around to give you any improvement. It is extremely suitable, though, when you have greenfield construction or even realignments. So those are really the 2 types of projects that it's best for. And then there's 2 types of optimization, vertical and horizontal. Now, vertical optimization is deterministic in that it actually will deliver a true optimal solution, the best possible alignment it can possibly do that minimizes the cut, fill, and earthwork movement costs. Horizontal, on the other hand, searches for a better alignment within your user-defined corridor. And it also relies on the repeated use of vertical optimization. So horizontal, it looks for this improvement, and it can also take quite a long time to do. So in terms of how it works, there's sort of 5 key inputs that we need in order to do an optimization. The first is your topo or your ground data. We recommend LiDAR if you have it. This allows you to, especially if you're looking at different horizontal alignments, really easily evaluate the different options because you have that area of high resolution data covering a wider range. We need a preliminary horizontal alignment, your cross-sectional geometry, so what your typical section looks like and how it behaves in different scenarios, and we set that all up in our cross-section template editor within RoadEng, your costs and constraints. And when we say constraints, we're really talking about your design speed or your K value, min-max grades, If you have, fixed control points, whether that is tying into a specific elevation or a specific grade, and material movement direction. There's a bunch of others that I think Matt will probably talk about when he's in there. That all goes into our optimization engine, and then we get three outputs after a whole bunch of fancy computational stuff that I am not technical enough to fully explain. But we do get our optimal alignment geometry, so a vertical alignment or profile that's been optimized, a cost, and something called an earthwork movement schedule that shows you how the different material types are moving, where they're moving, and the direction they're moving in. So some really powerful data, especially if you're doing something like a design build project, that earthwork movement schedule is really useful. Horizontal optimization, as I mentioned, it does sit on top of vertical. So you start with that initial hand-designed horizontal. The software then takes those same vertical optimization parameters and basically will iterate your horizontal alignment by moving around your IP points, optimizing it vertically, and looking for an improvement. Finally, I think I've got one more kind of technical note here. It's on costing. So we have a couple different costing pieces of information or data that we collect. So you input your rates for excavation, placement and compaction of different ground types, as well as your movement costs. Hauling and loading, we can set up different distances, free haul, overhaul, end haul, getting those in, and then the software is going to continuously update your expected costs. It does this when you do an optimization, and even if you make a change, whether that changes to your template, to your any of your alignments through a hand design change, I should say, it's going to give you changes in your costs so you can see the impact of different adjustments and different variables. Now, one question I'm sure we're going to get this in the webinar, so I'm going to just cover it off now. Even if you don't have specific costs that you can input or you're not 100% confident in them, as long as your costs are directionally representative of your true costs, for example, excavating and moving solid rock is a lot more expensive than overburden, then you can still use the costing data, even if you've got it roughed in there, to quantitatively compare options. Okay, lastly, and I'm sorry everyone, this is because I come from the sales and marketing team, I can't not put a slide in, just some benefits of optimization, why you might want to do it. We do see a typical reduction in subgrade costs in the area of 10 to 30%. We have seen a lot more, especially when we start working with horizontal optimization. It gives you the ability to automatically and internally balance your mass haul. You can save engineering time. So, freeing up additional time for you to be able to go and review other alternatives, this ability to automate that vertical alignment, as well as to look for the improvement in horizontal, really does save time. The ability to track and report material movements. We do it through something called the OptiHaul graph, and that's a really powerful set of data that really helps you handle your movement and movement directions. Quantitatively comparing your alignments and your design variables. For example, if you look at a road with a lower K and a higher K, how do the costs compare? What impact does that have to your construction costs? And then the last piece is you can actually really quickly check the feasibility of a preliminary design to see if it meets the criteria by running it through Optimal. And with that, I am going to pass it over to Matt.
All right, thanks, Erin. Yeah, thanks for the introduction, and we'll just jump right into our example. So the example today, I was planning on showing building a tin using two different data sets. So we've handled LiDAR and conventional survey data quite well, so we'll start out with that. So I'm just going to open up terrain. I'm going to start by inserting a shapefile for a preliminary alignment. So let's go with this one here. So our shapefile has a PRJ attached to it, so the projection's already set. And there we are. Now I'm going to use this preliminary alignment as a reference feature to thin our LiDAR data down to keep the file size small so it's easy to work with. Now I'm going to insert our LiDAR data. It's DEM data. I don't care about showing your extensive order, but for the selection, this is where we're going to use that reference feature. So I'm going to click Add Corridor. Let's make it 400 meters wide. Oops. I need to select my feature first. 400 meters wide. Hit OK. So in here, we're not going to skip any of the points. We're going to keep the full resolution of our DEM data. But outside of that corridor width, I'm not going to put the road there, so I don't care about having all that extra data in there. So we can get rid of it right on import. So we'll skip all the points. The projection, it's a TIFF file, I believe, that I inserted in there. So the projections attached to that, if they were in two different coordinate systems, the software would do the transformation for us. I'm going to hit OK. That's going to plug away and read that in a separate train file. Separate train. I'm going to bring in my total station data. So I will go insert. I want my, oops, I guess it's right here. Click open. And this is an IOP file. So this, I have it pre-configured to match my survey codes. So it's really easy to bring things in. So that ASCII file has the second column in it is my X coordinate, third column is my Y coordinate. We've got a point number as our first column and point code as our fifth column. Now those codes, example centerline, we can say anything that starts with centerline will be treated as a polyline. It'll be red, it'll have this dash line work. The actual shot points will have a triangle with them. It'll be treated as a break line and it'll connect adjacent by code. So that is if we had multiple CLs and if they were numbered CL1, CL2, for example, it's going to keep those CL1, CL2 features separately, but it will connect the CL1 points with the CL1 points and the CL2 points with the CL2 points. Similarly, we have ground, it's getting brought in as a point. Yeah, so that's that. Selection, we don't have to thin this test. We can make sure everything's being read in properly. And projection, since this is just ASCII data, it's not carrying the projection with it. I know that it's surveyed with real coordinates, and those are, actually in this case, they're UTM coordinates. So UTM zone 20 coordinates. We'll hit OK. And there we have it. So our survey is brought in. Now at this point, that survey is just lines and points. It's not a surface. So I'm looking in the 3D view. To turn that into a surface, I can go into my terrain modeling, click generate, and I can configure a few things. Now for this, I'm going to take this data and merge it into my LiDAR data. So I don't care about making contours. I'll just look at it and make sure it's reasonable in the 3D view. Maximum side length, I don't want a whole bunch of interpolation going on with this. So I think maximum side length is 30 meters. So maximum edge length on those triangle edges in my tin are going out there up to 30 meters. We'll hit OK. Check our survey, and that's looking pretty good. So now I'm going to save this. I'll just call it TS for TS survey. And before we go to that other, back to our LiDAR data, I'm going to do one more thing, and that is bring in some imagery. So we're dealing with data that has a real coordinate system. It's projected. So I'm going to select a feature here. I'm going to click Home, and I'm going to import some orthoimagery from the web. So here we have that. I know that preliminary alignment, if I had done it in my LiDAR data, it comes back to here. So I'm just going to crop this area. That's my area of interest. I'll hit save. I'll turn up the resolution. And that's going to download from the web. I'm just going to let that work in the background, and we'll jump back to our LiDAR data set. Our LiDAR data set has been brought in. That big pink blob was all the points that we brought in. So if I zoom in, we can see that points are on the DEM grid. If I click away from it, since they're not being displayed, they're still in the file, but we can't see them. Also, the width is going to be 200 meters either side of that reference feature. So this is good too. Again, this is just points at this point. Oh. And I'm being interrupted because that image that I'm downloading from the web is done downloading. So I'm just going to click save here. Turn up the resolution. And there's our image file. Right, back to the LiDAR. So here we've got our terrain calculation. I'm going to turn off contours. I'm just going to model it. We'll hit OK. And we'll click the 3D view, and there we can see our road. Now, I want to take actually we'll take Control A. The reason I have total station data for this one is we also have, we don't have the coverage we want with our LiDAR data. So just as those draw, we can see there's a pretty abrupt edge here, and that's just because my LiDAR tile doesn't cover that. So putting those two data sets together, I'm going to use the merge tool. So click merge. I'm going to browse to my PS terrain file. Click open. I'm just going to change a couple settings here. These settings, so if I leave those on, it's going to create a break line around both tins and there's going to be abrupt change. I'm just turning those off, so it's a little smoother edges between the two data sets. We'll click OK. There's that. So right now our surface is gone. We'll come back here and we will remodel, and this time it'd be nice to see some contours because we'll actually use this in our design. So let's go 20 and 2. I'm just going to check. Okay, good, that's not being modeled. So 20 and 2. We'll hit OK. That's going to take a moment to generate the surface, and then slightly longer to generate our contours. So the surface is already made. Now it's doing the contours, and we should have a tin with contours momentarily. So pretty good. Pretty easy to do. So yeah, right now where we're at, we've taken our survey data, so the total station data, we've created one surface. We've taken our LiDAR data, we've created another surface, and we've combined them to make a single surface. So this single surface is going to be what I'm going to use in our design. So file, save as, and I'm just going to call this topo. And I'm going to close out of terrain, and I'm going to switch over to location. So file, new file, browse. I want that topo surface that we just saved. Then I can choose whether I want my starting alignment to be based on a feature, based on a traverse file. But for this case, I'm just going to have that first point show up in our center of terrain. And click our alignment in by hand. Here we're asked whether we want to use the default template or an empty template. We'll use the default template. And my first point's out in space because that LiDAR tile probably had a corner out here. We'll move it onto our surface. And there we are. So now our alignment is just the first point. Before we get designing too much, I'm going to go into Plan Options, Background, Add, and I'm going to bring in that image. That image, there is a draw order here. If we leave it as is, the image is going to be on top of our contours, which isn't ideal, so we'll shift them up. That's that. Now I'm going to rough in my horizontal alignment. So this will be a two-click process. First I'm going to choose the Add IP tool, and I'm going to say let's follow the existing tangent of that road. So this is an upgrade example. Let's come out here, keep it fairly straight. And we've got a little bit more going on in here. Let's put that curve back here. And as I click this in, I'm only adjusting our horizontal alignment, but if I go over to my profile, like the zoom to extents, we can see we've got our draped topo surface right now showing up as we extend things along. So that's that. Now if we wanted to, it's weird what that was. If we want to optimize, we could right now. So this would be our horizontal alignment. Actually, first I should fit a few curves. So I'm going into the curves panel for our horizontal alignment. I'm going to add those in. My default curve is set to be a 250 meter curve. I can click this button, apply default curve to all my IPs. That's getting set up there. So there we've got our curves added really quickly. There's a few of these that I would rather use a smaller or a larger curve, so gentler turn. Change that one to 1,000. And that's looking pretty good. So if we wanted to, we could come over to the Project Explorer and we could do an optimization just based on that horizontal alignment. Just to create a baseline at this point, I think we're going to do a by hand design first and give us something to compare to. Let's put our IPs at the main locations. Planning on using 8% for our maximum grade. Then we've got fairly big fill through here. That is just a product of the ground we're dealing with. That's that. I'm going to fit curves to that as well. So 80 km/h curve, we'll hit apply. So this is calculating for our sight distance. If you just want to do the curve based on a K value or length, we can as well. Do that for this next one. So if we set that to turn off auto, we can either assign it by a specific K value or we can go by length. So here, let's say I want that to be 100 meters long. It's all right, so that's that. I'm going to kind of limit this now. So I want to chop my road off just where we start to deviate from the other one. So I'm going to use this corridor, delete range, and I want to delete all points from the start to station 220. don't want to rebuild a section of road that doesn't have to be rebuilt. Actually, let's go. There's that. Yeah, so we've got that. We can see our mass haul, we're running a deficit, so just the premise of trying to balance things quickly here by hand, I'm going to create some more cut. It's probably too much. And this is where things can become quite time consuming if you are designing by hand. Now, let's call that close enough to balancing for our example here. We'll go into our Project Explorer and let's recalculate. We're going to recost. This is showing us that that is expected to cost approximately $4 million to build. Well, cool. Let's see if we can do better using the optimizer. So we've got our by hand example here. We're going to click New Vertical Alignment. And this is where we'll start configuring how that optimization is going to take place. So this first tab in our vertical optimization options is kind of letting us choose what's happening in the optimization. So here we're going to say, let's sample our cross sections every 20 meters. So the software is going to do that optimization by sampling at a defined interval and figuring out what the cross-section area for a cross-section can be. That sample is going to take place within a vertical band. So down here in the vertical control, we're saying based on our band center being vertical alignment. If we want to just base it on ground, we can. That's why we can work with just a preliminary horizontal alignment if we'd like. And we can say, let's go 10 meters either side of that. So we're sampling in 20 meter intervals along the road, and then we're allowing the road location to be either 10 meters if we're using ground as our center, 10 meters of cut, 10 meters of fill at center line. Station range, we're going to do our total length of road, and then we'll come over to this one. So the standards tab is where we can define how things are going to our design standards. So here for our percent grade, we can say if you're in an industry where you have to worry about favorable and adverse hauls, you can have a separate minimum and maximum gradient. For this, I want my max grade to be plus or minus 8%. Then curvature. So I want to use a minimum K value of 35 for both crest and curves for this. If I was going with say a design speed of 50 kilometers an hour, I could give a sag of 12 and a crest of 11, and we'd account for that. If we wanted to have different design speeds along the length of our road for different sections, we could assign this for one section and then have a slower section of road in there as well. So maybe you were coming into a section with a difficult crossing that you wanted to reduce your design speed for, you absolutely could. Up here, the options are curves fast, so that's going to be where we don't force the alignment to have a vertical tangent between our curves. So this is a less constrained option than if we force tangents between those curves. So it's typically cheaper, but depending on your how many vehicles your road sees and how fast they're going, it may or may not be appropriate. We're just going to leave that as fast curves for now. And we'll come over to control points. So control points, we're saying that the alignment has to be at a certain location. So here, most common, especially for realignment here where we've got kind of a fixed point at the start and end of our road, we can say, I want a control point at the start of our alignment. I want to be at our ground elevation, so that's pulled in from the alignment that we're referencing, and I want one at the end of my alignment. So other common ones would be if you had a crossing that was designed and you wanted to be right at the abutment elevation, or junctions with other roads, etc., that you didn't want to disturb. So that's control points, pits. Won't go into too much depth on this, but I will just pull one in for example. So if we have a location along our alignment where if we have something where the cheapest option isn't a balanced road and we can borrow material from a pit, we can account for that. So we can say our pit is at a given station, so let's just station 1000, and we can say borrow material. So we can say that it's a gravel source. If there's a capacity, we can say that there's only up to 4,000 cubic meters there for material, and it won't exceed that for how much it borrows. We can also account for site prep as well here. So if there is a cost to open up that pit, if you're mobbing in equipment, or if you have to pay a landowner to use it, you can account for that. And then if you have multiple pit options along your road alignment, the software is going to account for that opening cost. And if it makes sense to only open one pit, even though opening all the pits is going to reduce your material movements, you can. So there's that. Waste sites behave similarly, except the opposite. So if you have a surplus of material that you want to get rid of and you're hauling it to a waste site, we can account for it there. We won't put a waste site in this one. Oh, and I obviously want I'm going to leave this as an infinite volume, so we're going to assume we can get all the material that we need from there. Now, this next tab is boiling down to, okay, our purpose of this optimization is to minimize the cost to build the road. Well, what are those costs? So here we can say, if we are excavating gravel, we can assume that gravel is going to cost whatever we want. So we can give it a unique cost for excavation. This one's $12 a cubic meter. And then we're saying the placement of that material is $4 a cubic meter. If we go to solid rock, as Aaron was saying, it's obviously going to cost a lot more to drill and blast. So it's costing more. The computer knows that it's going to make sense to avoid that if you can. So those different handling costs are unique to the material. You can use the same handling cost if you'd like. But yeah, you can capture the differences in them. When we go to our movement costs are shared amongst the different material types. And here we can break down what's considered free haul, what's considered overhaul, what's considered end haul. So this unit cost control is going to, if we adjust the numbers here, if you've got good unit rates, we can hit update, and it's going to adjust where those category breaks change. So usually that's representing different equipment handling the material differently. So this setup would probably be a dozer, and then maybe a scraper, and then a truck hauling. If you're working with something that's a little more constrained for the equipment that you're using, this free haul control option makes a lot of sense. So here we just say that it's dealing with two categories, and if we were dealing with a single excavator and everything other than that for excavation takes place in a truck, you can say 30 meters outside of that, it's all treated as overhaul. Just going to leave this as our default values and go on to the next tab. So here we've got our constraints. So this is adding a little more realism to the design. We've got our direction. So if you want material movement to only go ahead from station 1500 to let's call it 3000, we can account for that. Similarly, if you only want to move backwards, if you're dealing with steep terrain and you can't build up off the ground, or if you can't move material ahead with a push, or we don't have preliminary access in, we can account for that as well. Over here, we have our sidecast tab. So this behaves similarly to a waste site, but it's more of a linear waste site. So here we can say, we'll allow the material to get rid of extra material along the edge of a road, but the unit that we're going to use for that is volume per linear length of road. So this, let's say we can sidecast 5 cubic meters per linear meter of road, and we can apply that along our entire alignment. If it makes sense, we can also do an auto-generate, where we can say that anywhere that our side slopes exceed a given value, it's going to automatically populate this and break it down into a table. So sure, let's allow linear sidecast for this. Minimum fill, if you're dealing somewhere where you have to overland, we can capture that in here, and that's going to get right in the constraint where, say, from station 100 to 200, I want a minimum fill depth of 1 meter, and you can capture that. I'm not going to use that for this example, nor am I going to use full bench, but full bench would be somewhere where if you don't want any material to be used as fill in your cross-section, the entire prism to be founded on cut, you can capture that here. And then minimum cut behaves very similarly to full bench. Just instead of being a hard constraint, you're saying that your center line has to be below a certain elevation. So optimization parameters, we can jump to this max resolution time. So if you had something really long and for some reason you didn't want it to run any longer than an hour, you could write that in. Optimization gap would be if you didn't care if your solution was fully optimal. So the default parameters, I think, is within 0.1% of optimal. You can adjust that. I don't see much of a use to adjust this just because there's also a cancel button. As this runs, you can abort it if it's not going fast enough or if you want to change something. Then display tab. This isn't really related to the optimization. It's just referring to when you can see this alignment. So, and then log is going to tell us if there's any issues. So we've got that set up. Let's go to our, so it's set up. Now we're going to run it. Run. So right now it's doing the sampling process. That's probably going to take a couple minutes. As we go through the next steps here, I'm going to jump to something that's prepared. And I will.
Hey, Matt, while that's processing, perhaps you want to answer one of the questions. We've got a couple in here. Can you define unsuitable material locations to avoid?
That's a good question. Once this gets finished up, yes. So I didn't touch on material types really at all. Right now I'm just going with the default parameters. And once this, actually I'll open up another design. I can talk about that while that runs. I'm just going to cancel that for now, just so we have access to what's going on. So for dealing with different material types and avoiding material types, the computer's quite smart. It can be as complex as you want to make it. So in that previous example, I just left my subhorizons to be all the same. I talked about the costing parameters in there, but I didn't adjust it from the default parameters. So what these are is our material types, and I can say from, let's go gravel, assume the material is gravel, over, let's go over fractured rock, over solid rock. We can give it a depth of Let's go 1.5 over 2.5. So this is 1.5 meters of gravel over an additional meter of fractured rock and then solid rock. We can apply that. We can apply it for a certain section. So if we want to go from the start of our alignment to station 200, we can, and then it goes to the default in this case after that. Or we can apply it for the entire length and after that. So that's defining the material that's at site. For fill types, we can say what material is actually getting used, or we can say that there is a quality component to that. So if we want to make sure that we have really good material from location, let's go with gravel. So if we want to say we have fairly good material in this case, from station 400 to 500, we can do that. And then it's going to know that material has to be at least quality level 3, because it's replaceable here. Now, when I say quality level 3, I'm referring to this costing tab over here. So here we've got a quality factor built into our material types. So our hard pan material is Q2, so that's not as bad as overburden, Q1. Gravel's Q3, so it's pretty good, whereas we go up to solid rock, that's our best material. So where we've assigned gravel, we can have Q3 or better materials. But yeah, you can account for it there, and then the computer is going to take that into account for your balancing, consider those quality requirements as well. Hopefully that answered your question. This has run its optimization. We'll hit OK. And set this as current, and we've got a cost of $1.5 million-ish. So that original one was a lot more. So now with this, this is a fairly fast road. It might not be ideal to have this fast curves option here. So we've got a bunch of curves right on top of each other, but they're still adhering to our design constraints for K value. So yeah, we shaved off a bunch of costs. That's excellent. If we wanted something with a little more, well, with space between our curves, then we could go through and use the variable curves and tangents, for example. So this one, we're going to have a minimum distance between our curves, and then adhere to those K values at our curves. Other options here, a nice one to use is this user defined. So if you picked out the locations where you wanted your IPs to be located, the computer's going to move those up and down. It's not going to add extra ones, though. Nice one to fall back on. Yeah, so that's a very quick example for this. If we want to finish our design right now, we could go over to the multi-plot page, grab our book layout, and put together our design. So there's that. If we want to compare options, using the optimizers is a nice way to compare options. Just if oftentimes if you're clicking around by hand, it's easy to do a really good design with one of your options and kind of click it, maybe not give it the attention it deserves for another option, and that's going to affect your costs too. So using the optimizer really standardizes how well that design takes place, and we can see that between this one and this one, we're looking at a significant savings. So let's do a compare with current. We can see the two costs broken down separately. So that's great. Now I'm going to jump to the cooking show approach, where I'm just going to show a few other options. So this is our one that I've already run through. So here I've got by hand design. I've got, oh, and I've moved the alignment around since then. Actually, let's just jump to it, and we'll go back to this one. So this is, I believe, a variable curves and tangents option. So this was optimized. I used the variable curves and tangents, and now we've got tangents between our curves. So if we go in here, we look in our vertical options. My standards for this one are set to variable curves and tangents. Each of my curves is going to be a minimum length of 80 meters. Each of my tangents is going to be a minimum length of 80 meters as well. Yeah, so that's the big difference between these two. Another thing that's worth considering, the way I ran that first optimization was it's optimizing your subgrade construction. So unless you tell the computer to take into account these other materials, so my subgrade being down here, and I have my subbase, base, and asphalt layer, it's just adjusting your alignment to balance your subgrade. If you want these costs to reflect those extra materials, I've done that in here. So I've gone to templates. I've chosen I can hover over, I guess, first and see, okay, that layer is being counted as surface layer 1. That layer is being counted as surface layer 2. And that layer is counted as surface layer 3. I can go to my materials and I can say surface layer 1 is going to be a given material type. So if we're dealing with local materials, we can account for that with whatever we want in our list of materials. In this example, I've added a few extra material types here. So these are your manufactured aggregates. So I've got a 1-inch minus, I've got a 3-inch minus, and then I've got my asphalt. And obviously these are going to cost a lot more than dealing with local materials for my subgrade. So I've accounted for that. Saying my 1-inch minus costs $24 cubic meter to produce. And then my ASP is going to be that, well, that's my actual asphalt. So it's going to cost a big number per cubic area. So I've included that in here where I say layer 3 is my ASP, layer 2 is my 1-inch minus, and layer 1 is my 3-inch minus. So that's why we've got a significantly larger cost here than the example I was just looking at. And that makes sense. Most of the time, if you're optimizing your vertical alignment, the surfacing cost is a fixed linear cost. There's not much variability to make it better. Where that becomes much nicer to consider is if you go to a horizontal optimization, where having a shorter road as savings. So using that as our segue into the world of horizontal optimization. And I'm not going to run through a full example here. I'm just going to show a quick example. So if I want to optimize that alignment, I can do it right in here. I'm just going to do a new one and get it set up. So horizontal alignment 3, I want to make it a duplicate of my horizontal alignment 1. And then in my options, I can choose how that's going to behave. So for this one, we'll look at our design a little bit closer. As we get out to the end of our alignment, I've got a crossing site here. I've got some steep slopes with a river at the bottom, and I'm tying into the existing alignment. So I'm going to treat that as fixed. So I don't want to optimize the whole thing. I just want to optimize what I can without a significant, without running into a bunch of complexity. You can account for that by adding in constraints and trimming tins, but I'm going to assume that end is good, and I want to move around this. There's lots of space to move this guy around, and this one will assume it's okay to move around as well. So I'm going to come in here, horizontal optimizations, and I'm going to say, let's move horizontal IP. So our first IP is back here, second IP, and third IP. And they're also numbered C3, for example. So I want to optimize my third and let's go with that. And let's go X and Y offsets. So let's go 200 meters and a Y offset of 600 meters. We'll hit OK, hit OK. And that's giving me a box where we could move that IP around to. Now, if we go back to this and change this orient grid, now my X and Y's are relative to the alignment of my road. Y being along the length of your road and X being crossways along the road. So there's the areas that can be moved around. And if you don't include a material cost for your cross section, so if you didn't do that first thing, you could also just account for a per length cost for your surfacing if you'd like. So I don't need to do that here because I've already accounted for it in my materials. Yeah, other than that, if I wanted to only shift those IPs crossways along the road, I could go with the perpendicular only. And that's the area that I can get moved around to. So I've run this, and this is the alignment that it came up with. And of course, I ran it just before our demo and realized that I didn't really account for something that I should have. So here you can see my alignment is cheaper than the previous optimized vertical alignment. So I go from that one to this one. But I'm going right through a few buildings. So a workaround to get through that would to be clip that area out of your tin so there's no surface there so the road doesn't want to go through it. But yeah, it's pretty powerful, pretty useful software. It's great as it's great to do your design. It's also great to check your design. So for this one, I've got my preliminary alignment in, or close to my preliminary alignment in there, then I optimized it, and I can see, well, it wants to make this as short as possible, just driven by the cost of my surfacing. Now, I can see that's right to the edge of my tin. If I had, now I'd probably be considering, well, maybe it makes sense to realign from back here and get away from those houses, but really make that as short of a route as possible. That's what I've got. I guess we'll go back to
Awesome.
questions.
Thanks, Matt. A few more questions here in the queue, and for those of you still, with us, please do, keep typing them in. The next question: how would you enter constraints for a bridge in the middle of an alignment?
Okay. So this one, I just ignored it, just for the sake of demonstrating. But let's turn this on. So another thing, so ground types, I kept it as simple as possible starting out as well. So if we have different templates for bridges, say you're not cutting and filling through a waterway, which makes a bunch of sense, we can account for that too. So in here, assigned by range, I can use different templates for those different sections. So in this one, I've got my default template. I've got a barrier template, which is different, but I did apply that for a certain section of road where I'm going through a large fill. So I've got my barrier there. So similarly, we can apply a template where we don't have a bridge going, or where we have a bridge going. So it would just be a matter of assign by range and using the bridge template. So this bridge template is a no cut, no fill. So it is just a blank section of road, which is what I've used here. So no cut, no fill. Zoom out, it's just a floating line. If you want something a little more graphically pleasing, you can go to your templates, you can grab something off the library, and build a bridge cross section that isn't showing fill below it, but you can still account for your superstructure. From an optimization standpoint, this would be a section where I guess it depends what governs, whether the road alignment governs or if your hydrology clearance governs. If your road alignment governs, I'd design and then fit the bridge to that. If you had a bridge that bridge that the abutment locations were really important, then that's a location that's already designed. That's where I would use the control points. I'd set my control points at either end of the abutment, so that goes through there. All right, next question.
Okay, next question. Does the optimizer only optimize the centerline locations?
So by default, yes. It's undulating the centerline alignment or adjusting it horizontally, assuming a fixed cross section. I believe we're planning to do just an example webinar in the future where we're using some of the version 9 features, such as using reference alignments. So I'm just going to pull this in. I won't do it, but I'll explain roughly what it is. So here I've got a vertical tie, so I can attach that ditch alignment to another alignment, and I can further reduce my subgrade costs by treating this ditch as a variable alignment that can be used to address my subgrade requirements in the roadway. It's kind of having a optimization loop in there and using one to make the other cheaper. So that's an entirely separate webinar.
Excellent, and let's tackle one more. Just a note for everybody else, if you have more questions, yeah, still send them in. We will answer them over email, but we're approaching the end of the webinar. So let's do, which one do I want to do? How does the software calculate cost for sidecast?
So cost for sidecast, that's a good question. Sidecast is, that's our kind of linear spoil site. So that's assumed to be your free haul. So it's just the handling cost assigned to that, assigned to that movement. So it's your free haul handling cost for that movement. So it's right there, descriptor.
Perfect. Well, thank you, Matt, for tackling this live demo. Thanks, everyone, for attending today. We hope you got some great information on optimization to help you better understand what it is, how you use it, and how you might benefit from it. If you have any other questions, please feel free to email our support team. They would love to answer them. That's support@softree.com. Otherwise, have a great rest of your day.
Thanks for watching another Softree webinar. Please be sure to subscribe to our channel below or tell us that you liked the video. Thanks for watching.